Welcome to the final video lecture of new material. I'm very clear about that. So this is the last one of the year that we'll discuss new topics. In this one here we will cover fission and fusion and their nuclear reactions. This will follow along in chapter 32 and we will wrap things up. So let us begin. Before we get into the individual reactions, whenever we're doing any type of nuclear reaction, we need to make sure that we always conserve our mass and energy. This can be done through making sure that we, at least for these nuclear type reactions and not nuclear decay, we need to make sure that there is the same number of particles before as there are particles after. So here we have the same number of protons before as we have after the reaction. We have the same number of total particles before 11 as we have after 11. So it's important to understand that we need to make sure that there are consistent numbers throughout any of these nuclear reactions. In fission, what happens is a nucleus of some sort breaks into possible or splits into multiple different nuclei, or all the other particles, I suppose say that. One example, and one common example, is uranium-235. When you add a neutron to it, it will become an unstable uranium-236. This will decay into, or not really decay, but it will break apart into multiple different particles or atoms. This just happens to be a couple of, one sample of one thing that it could break into, barium and krypton. And there also will be a lot of energy release, and this energy is in the form of gamma rays and other types of radiation. And a lot of it goes into heat and thermal, as we'll see in a second, it goes into heat. There also are a couple extra neutrons released from this process, because we need to have conservation of particles within this here, because this is not a decay process, but just the splitting of one molecule or one element or atom into others. And what happens is you get this idea of a chain reaction, because those extra neutrons go on and hit other U-235 or uranium-235 atoms, and then they continue to break apart. And so you get this continuing process here. And we'll see in a second about how you control this. Before we go back into the chain reaction, just a little idea, because you're all thinking about how a nuclear power plant works. Maybe you're not all thinking that, but it's somewhere probably floating around in your brain. So what we have here is we have a reactor, and I'll come back to that in a second. And through the process of fission, it heats the water, and that water is pumped into what's called a heat exchanger. And that heat exchanger takes the water from, and this is kind of the hard water, you could say, the radioactive water from the tank, and it radiates that water into, not the radiation though, but it radiates that water into the heat exchanger. That water evaporates into steam. The steam then turns a turbine. The turbine turns to an electric generator. Boom, that goes through a condenser. So there's a lot of energy. There's a lot of energy transfer. It needs energy to condense that steam, so it heats up. So there's a lot of heat transfer going on here. And then it goes back into that water, goes back into the heat exchanger, and it continues that process. Now, almost all electricity is generated this way, whether it's through a nuclear reaction or coal burning or burning of natural gas or wood chips or burning of whatever. But this is the general idea. You just take the reactor and put some other heat source over there to heat up the water. That's probably about almost all power, except for hydroelectric and photovoltaic. Everything else is done through this type of process. Even geothermal energy, they use that geothermal energy to heat the water to spin turbines and go that way. This is the basic method for how all power plants are run. When you have a fission reaction, you need to have something that controls the reaction, and what it does is it absorbs that extra neutron. And generally in nuclear power plants, these are called they're sometimes called cooling rods, and what they do is they lower the amount of fission occurring, and they absorb the neutrons happening. Or you have the certain type of material that you insert into where the reaction is occurring around the plutonium or uranium or whatever you're using here, a fission reaction, to make it absorb the extra neutrons. And one example is cadmium. I know those are used as certain control rods, and they absorb the extra neutrons. Whereas if you didn't absorb the extra neutrons, you'd have this idea of a chain reaction where if one uranium atom absorbs a neutron and it just splits off with three, and then those three go and absorb and hit other things, and those split off. And what happens is with barium and krypton or most of the other molecules that you produce as the byproducts of this, along with those extra neutrons, is they are very neutron heavy. There's a lot of extra neutrons, so they undergo beta decay of some sort, and there's even more energy released in that. So within a certain nuclear reaction here, within fission, there's constantly energy being released through maybe not just the first parent interaction, but a lot of the other second daughter and third, or whatever you kind of call it, however you describe it, different lower generation nuclear reactions here, as it goes through and splits apart and then goes through some sort of radioactive decay. As we've already talked about, fission is the splitting of atomic nuclei, whereas fusion, as you might expect, fuse, come together, is the joining of two nuclei together to form one larger singular nuclei. This occurs where you have, it depends really on the binding energy, where you have two things, two materials that have a lower mass than a smaller nuclear mass than the product, and the binding energy is related to the amount of energy released. But what they do is they fuse together and form this heavier particle, but each heavier than each individual particle. Now, there are a lot of energy released with this. Now, this is generally happens on a large scale within stars and other certain bombs or explosives here on the Earth. But it's the amount, you need a lot of pressure, heat, and everything else to have this begin to happen within a substance, or within anything, especially within stars. Deuterium has an atomic mass. This is basically, you could say hydrogen too, but it has deuterium has an atomic mass of 2.014. I'm going to leave off the last. And tritium has an atomic mass of 3.016, or hydrogen 3. And when those combine together, they form a helium atom, helium-4, which is has an atomic mass of 4.002, and this is all in atomic mass units. And that difference in mass right there of almost 1, which goes into the neutron there too, but there's also a difference in the total amount, if you were to actually carry it out, that relates to the amount of energy produced. And so there's massive amounts of energy produced when this happens. But the conditions for this to occur they really only occur when you have, like, for example, as I mentioned before, in stars or in the hydrogen bombs. Most actual nuclear bombs that we use or have used in the past are fission reactions, and this one here, we very rarely have fusion going on. So it's really just the fusing of two different nuclei together. And actually, one of the interesting things is for things below less than iron, when they fuse together, they release energy. And for things with more mass or greater than iron, when they fuse or undergo fusion, they absorb energy. And it's actually the opposite process for fission, but we're not really going to go into that too much. So this is fusion. This is the end, pretty much the end right here. So, yeah. And that just about wraps it up. So there is the end to the new material that we will see in this